Okay, so we are moving to um, section chapter 7, and this is Cosets and Lagrange's theorem. Okay, and Lagrange theorem, which in because we're actually not going to get to rings, but we will be able to finish up groups. And so Lagrange theorem is one of a famous theorem in group theory, and it basically says, so it says if G is a finite group, okay, and H is a subgroup of G, then the order of H divides the order of G, okay, and we know about this with cyclic groups, but this is saying for any finite group we choose that this happens. But before we prove that, we have to talk about cosets. So for the following things that we're going to do now, assume that G is a group and H is a subgroup of G. Let A belong to G be a fixed element. So if you're going in the book probably will give you a little more information, which is fine, a little more details into these definitions and things. But because of time and class and things of that nature, I'm sort of highlighting the main element. So you still should read the book to get even greater insight. But I will definitely give you a good foundation of the definitions and the properties and things, and try to do some different examples from the book so you can also use the book examples. Okay, so we have that. The set AH is the set AH, lowercase h, where H belongs to big H, okay? And this is called the left coset of NG, so we can sort of highlight that. The left coset of H in G containing A, and the set HA, which is equal to H, um, here HA, where H is an element of big H, well, H is a big element, is an element of big H, is called the right coset of H and G containing A. All right. Also note, if the operation is addition, we write A plus H and H plus H to represent the left and cosets, the left coset and the right coset, respectively. Okay. And okay, so you'll know that's representing the left coset, and this is our right coset. Okay. And in general, oh, I'm sorry, I haven't got there yet. So number two, so that's number one. Number two, if G is a billion, then A of H, the left coset equals the right coset. Okay. In general, however, we won't necessarily have that property, but if it is, then know that once you do the left cosets, once you find all the left cosets, you found all the right cosets because they're equal. Okay. So we're going to look at example one, find all the distinct left cosets for this, and B. So we're going to look at some examples before we get into the properties of cosets. Example one, find all distinct left cosets A, H, for all A belonging to G, for H equals the cyclic group generated by 6 and Z10 under addition mod 10. Okay, so first, let's figure out our elements in the cyclic subgroup generated by 6. And this is under addition because we're in mod 10. And we can start with 6. You can start with 0 if you want. So 6, that's 6 to the first, right? 6 squared is, since we're under addition, is 12, which is congruent to 2 mod 10. And then to the third, 18. So that's 8. To the fourth is 24. That's 4. And 30, which is 0. Okay, so we have 5 elements here in the cyclic subgroup generated by 6. Now what you do, it's really up to you, because if you go back to the definition of cosets, A is some fixed element of G, right? And so the set AH, basically you pick an element A and G, right? And then you compute it, however, whatever binary operation you're under. Here we're under addition, right? And so let's start with 0, okay? But you really can start with any number you want in Z10 to start computing the left cosets. I mean, there is a systematic way, and we'll talk more about that when we get into properties, but let's just start with 0. So 0 plus, and I know I'm going to need some room, so I'm going to come to the edge over here. 0 plus h, well, that's equal to 0 plus, and I'm only going to sort of do it all the way out for this first one so you understand what we're doing. So I'm picking 0 because that's an element in Z10, right? 0 plus H is equal to 0 plus the cyclic subgroup generated by 6, which is equal to, let's do it like this first, 0 plus 6, 2, 8, 4, and 0, which is equal to, this is 0 plus 6, 0 plus 2, 0 plus 8, 0 plus 4, and 0 plus 0. Well, that's just going to give us 6, 2, 8, 4, and 0. So we notice we get back H here, right? We just get back H, which is the cyclic subgroup generated by 6, okay? Let's go to 1, okay? 1 plus H, see what happens. So for 1 plus H, we'll have, I'll do it like this, 1 plus 6, 2, 8, 4, 0. All right, so that will give us what? 7, 3, 9, 5, and 1. Okay, just adding, right? And let's see if we do 2 plus H. Well, that's 2 plus 6, 2, 8, 4, and 0. And so that's 8, 4, 10, which is 0, 6, and 2. Well, what is that? That's just taking us right back to H, right? So now we notice that we are repeating. And the question asks us to find the distinct left cosets of all the distinct left cosets of this particular group. So we can conclude that there are only 2 distinct cosets. All right. And what we notice is that, well, we'll see when we get to the properties of cosets, but really, remember what group you're in. We're in Z10, right? So what's the cardinality of that? It's 10. So once we realize, well, in 0 plus H, so we already have 5, we have 5 elements out of our 10, and then 1 plus H gave us the remaining 5, right? So we really could have stopped there. I just wanted to show you that if you were to pick another element, it's really going to be in there. And we'll look at that in terms of properties. As a really nice property, some nice properties hold with cosets that we'll look into. Okay, but let's go ahead and go to part B. So in part B, we're in S3 now. Okay, so let's recall. And I'm going to just make a tiny bit of adjustment here. I'm going to, let's call that E, okay, which is, we know the identity. So recall, for S3, the elements are, well, E, okay, which is just the cyclic, that one cycle, right? 1, 2. We're using, from here on out, we're probably going to be sticking to cyclic notation. If you're still not comfortable with that, then just go back over some problems we did to become a little more comfortable with that. Okay, so that's S sub 3, right? And now we want to find the left. Again, we're trying to find all the distinct left cosets. Okay, well, let's start with E. All right, EH. Well, that's just going to be E, I guess E composed with itself, or if we want to make this 1. Let me see if I use 1. I think I used the 1, but if you want to use E, you can. And then E composed with 1, 2. Well, you know the identity just gives you back whatever that is. So that's E, and that's 1, 2. Okay. And let's see, I think I want to use, what do I want to use? Maybe I'll use 1. You can use E, it doesn't matter. Okay. So we have H. Interesting. I wonder now, from A and B, do you see something? See something that's going on, which we'll talk about with properties. Okay, well, let's go. Since 1, 2 is next on my list, let's try 1, 2. So 1, 2, right? H. Well, that's going to be 1, 2 times 1. I'm using 1, I guess, or you can use E. Comma, 1, 2, 1, 2. All right, well, 1, 2 times identity is just going to give us back 1, 2. And then since 1, 2 is a transposition, we know if we compose it with itself, we get back the identity. So again, we see that we get back H. Okay. Well, let's move on. So now let's look at 1, 3. Okay. So 1, 3 composed with H. So 1, 3, H. That's going to be 1, 3, 1, comma, 1, 3, 1, 2. All right, so we get back 1, 3, put a comma there, comma, 1, 3, 1, 2. So let's see, 1 goes to 2, right? And then what happens to 2? Well, 2 goes to itself. So that means we have 1 goes to 2. Okay. And then 2 goes to 1 and 1 goes to 3. So we have 1, 2, 3. And if you want to check to make sure that cycle closes, you can. We know it's a group, so it has closure. It can't be something else. But just in case, 3 goes to itself and then 3 goes to 1. Okay. And okay, so that's the coset. All right. Now let's look at 2, 3. Okay, so 2, 3 times H. Well, that's going to be 2, 3, 1, comma, 2, 3, 1, 2. All right, so we get back 2, 3, and then let's see what happens. Well, 1 goes to 2 and 2 goes to 3. So 1 goes to 3. And then 2 goes to 1 and 1 goes to, I'm sorry, not 2, we're looking at 3 now. 3 goes to itself and then 3 goes to 2. Okay, and then just to close that up to make sure we're good, 2 goes to 1 and 1 goes back to itself. So the cycle is closed. Okay, so that's 2, 3. Let's move to 1, 2, 3. 1, 2, 3. You might see something already, but let's see what happens here. 1, 2, 3, 1, and 1, 2, 3, 1, 2. Okay, well that's going to be 1, 2, 3, and then you might can figure out without even computing what it's going to be, but let's see if you're right. If you see something's going on. Well, 1 goes to 2, right? And then 2 goes to 3. So 1 goes to 3. And then 3 goes to itself and 3 goes to 1. So that closes that. But if we look, we have what? We have the same thing as the left coset. So this is equal to 1, 3H. Okay. So we're actually done, right? Because S3 only has 6 elements and we have H, so that's a coset, right? And then 1, 2, well 1, 3 I should say gave us another because we're looking for distinct left cosets. So 1, 3H gave us another one, and then 2, 3H gave us another coset, another distinct coset as well. And then if we were to take, we're almost done really because we just need to do, if we wanted to compose 1, 3, 2, but it's going to be a repeat. And just so we can pacify those skeptics out there, let's go ahead and do it since we only have this last one to do. Okay, so now you definitely don't have to do this in general because once you obtain all of your elements, then you're done finding all your distinct cosets. 3, 2, 1, 2. All right, so H equals, let's see, well, that's just going to be 1, 3, 2. And according, if our theory is right, we should end up with 2, 3, right? Let's see. Well, 1 goes to 2 and 2 goes to 1. So 1 is going to itself. So when it maps to itself, we can omit that, right? Then, so let's go with 2. 2 goes to 1 and 1 goes to 3. So 2, 3, and then we can check that we don't have anything else. 3 goes to itself, and then 3 goes to 2. All right, so like you all probably figured out, we got back the left coset 2, 3H. Okay, and I'm gonna make that complete. So thus, the 3 distinct left cosets are what? Well, H, of course, and then 1, 3, H, and then 2, 3, H. Okay.